Hey everyone, welcome to today's Explainer. I'm your teacher, and we're going to make absolutely sure you are 100% ready to ace your final exam on atomic models. So grab your notebooks, get focused, and let's dive right in. Here's a quick look at the roadmap for our review. We'll be defining the atomic model, looking at the early models, exploring the nucleus and energy, jumping into the modern quantum model, and then finishing up with a final exam practice quiz.
Section 1. Defining the atomic model.
Okay, you'll definitely want to write this exact definition down. An atomic model is basically a way to show or explain what an atom looks like and how all its parts are arranged. We literally can't see atoms with the naked eye, right? So these models act like maps for us. Understanding this is absolutely crucial. It's the key to unlocking everything else on the test. Moving right along to Section 2, the early atomic models. So if we look at the timeline, we start out with John Dalton's super simple solid sphere model. He basically thought the atom was just a tiny, unbreakable ball. But, well, it really didn't take long for Thomson to come along and complicate things a bit with his plum pudding model. The really big evolutionary leap here is that Thomson actually found electrons. This meant Dalton's old idea of a completely solid, indivisible ball just had to be updated. Now we had these scattered negative charges stuck inside a positive sphere. Think of it kind of like chocolate chips scattered inside a ball of cookie dough.
Section 3. The nucleus and energy.
Science never really stands still, right? Soon enough, Ernest Rutherford came along and discovered this small, super dense, positive nucleus. And this was a total game changer. It proved that Thomson's giant positive sphere idea was actually incorrect, and that electrons instead move around a really dense central core, with mostly just empty space in between. Building straight off of that, Niels Bohr took Rutherford's basic nucleus idea and really organized it. He proved that those electrons don't just float randomly around the core. Instead, they move in these fixed energy levels, or shells. It's actually exactly like planets orbiting the sun, which is, of course, why we call it the planetary model.
All right, Section 4. The modern quantum model.
Now, for the exam, you absolutely must remember that in Erwin Schrödinger's modern electron cloud model, Bohr's fixed, predictable planetary shells are replaced by these blurry, cloud-like regions where electrons move. In reality, we actually cannot know exactly where an electron is at any given split second. We only know the mathematical probability of where it might be within these fuzzy clouds. Section 5. Final exam practice quiz. All right, close your notes, folks. It is time to test those higher-order thinking skills. Let's look at our first scenario. Say some students at a science exhibit in Bohol are crushing a piece of chalk into smaller and smaller pieces. One student points out that each tiny piece is still the exact same matter. Based on what we just reviewed, which evaluation best shows why Dalton's early model was a useful explanation for this? Well, if you guessed A, excellent job. Dalton's main contribution was introducing this foundational idea of tiny particles. Even though he had no clue about electrons or the nucleus yet, his solid sphere concept correctly hit on the fact that matter can be broken down into these fundamental, tiny building blocks. Next up, we're at a TV repair shop in Pampanga looking at a bending cathode ray tube. The beam inside is visibly bending toward a positive plate. So what conclusion is most supported by this specific piece of evidence? Think back to what negative and positive charges actually do. And the correct answer is B. Because that beam bent towards a positive plate, it practically proved Thomson's theory that there are smaller negative particles, electrons, hiding inside the atom. Remember, opposites attract, so that negative beam was completely drawn to the positive plate. Moving on to Baguio. Here, students are rolling tiny steel balls at a thin foil model. Most of the balls pass right through, but a few of them bounce sharply backward. Which explanation perfectly fits these highly surprising results? You are for sure going to see this on the exam. The correct answer is C. This brilliantly illustrates Rutherford's discovery. The fact that most balls passed right on through means the atom is, well, mostly empty space. But those very few that bounce back, they directly hit that incredibly small, super dense, positively charged nucleus. All right, question 4. We're looking at some amazing fireworks during a festival in Manila. The teacher notes that specific colors appear when electrons gain or lose exact amounts of energy. Which of our models supports this idea? The answer is C, which directly validates Bohr's planetary model. Remember, Bohr introduced those very specific fixed energy shells. When electrons jump between these fixed shells, they release exact amounts of energy, which we then see as specific colors of light, just like those beautiful fireworks. Last question. A computer simulation at the Philippine Nuclear Research Institute shows a blurry, fuzzy region around a nucleus where an electron is likely to be found, rather than a single fixed path. Why is the quantum mechanical model the absolute best fit here? The correct evaluation is C. For the final tomorrow, you really need to remember the key phrases probability clouds and orbitals. That will help you easily identify Erwin Schrödinger's modern atomic model. It's just not about perfect, neat circles anymore. It's all about the mathematical probability of finding an electron in a fuzzy cloud. The absolute most crucial takeaway today is understanding this entire progression. I highly recommend taking a mental screenshot of this summary before you walk into your test tomorrow. From Dalton's solid sphere, up to Thomson's plum pudding, then Rutherford's nucleus, Bohr's planetary shells, and finally Schrödinger's electron cloud. Knowing exactly who matches with what is a guaranteed point score. We've seen just how much the atomic model has evolved over time. Going from a simple solid ball to a complex, blurry cloud of probability, we really have to wonder, what completely new arrangement will scientists discover next? Keep that curiosity alive. Good luck studying tonight, and I just know you are going to absolutely crush this final exam.